this is what you'll see in the book. You can get electric field from potential, and it's the derivative of electric potential, V in volts, with respect to space. And we did this in the lab, and there's a negative sign here, which is pretty important, but just for the sake of it. More formally, however, like I said, this is a three-dimensional thing. So electric field is usually a three-dimensional field, and therefore, in order to get three dimensions from a scalar, we have to have this crazy three-dimensional derivative. And the way this works is this is a partial derivative of the potential with respect to x in the x direction, and then you take another partial derivative with respect to y in the y direction, and you continue with z. So that's how you contain a three-dimensional vector value for electric field within one scalar by doing this 3D derivative. You can also write this in spherical and cylindrical coordinates, and here it is. You don't actually need to know this specifically for this class, but it is very useful because remember, we are talking about three-dimensional things. Specifically, we're talking about taking those two-dimensional lab drawings and turning them into these three-dimensional vector fields. So how do we go from potential to electric field? Well, so a very interesting analogy to start with when we're talking about electric potential would be sort of topography. And if you have ever done any hiking and have looked at sort of trail maps, topographical maps give us a way of visualizing a three-dimensional space in two dimensions. And often when we're dealing with vector fields like an electric or magnetic field, and so far we've only dealt with electric fields and to a lesser extent gravitational fields, one tool for visualizing something 3D in a two-dimensional space is by sort of translating it into this kind of map. So the main thing here is when we're talking about vector fields, we're going to talk a little bit about the gradient. And the gradient is just the sort of derivative, it's a three-dimensional derivative of a vector field, or sort of the topography of a vector field. And once we take the gradient of the potential, we'll get electric field. Now the whole point of doing this is that although it's very easy to conceptually understand electric fields, or it's easier to conceptually understand electric fields, it's very difficult to measure them. And this is why when we do the lab, we don't actually do any direct measurement of electric fields. We do have a lab where we have a direct measurement of an electric potential, and that's because that's voltage, right? So we have all kinds of tools for measuring voltage, and we have lots of things measured in voltage because that is the easiest way to go about it.